All right, good morning and welcome to this week's edition of Boundaries Webinar Wednesdays. Today we're going to be covering Creo Simulate for linear and thermal analyses. And without further ado, let's jump into the content. All right, so today we're going to go over a quick introduction here. We'll introduce Boundary Systems, who we are and what we do, and also then talk a little bit about Creo Simulate, some of the capabilities of the kinds of analyses you can do in Simulate. And then we'll get into a software demonstration where we show you some examples of those kinds of analyses and simulations. And then finally, we'll get into a question and answer session. All right, so just a little bit about Boundary Systems. We are a product development consulting company based out of Cleveland, Ohio, but we have a footprint that affects companies way beyond the borders of Cleveland. We've helped many of our customers, achieve better and higher levels of success in anywhere from, CAD data management or product lifecycle management, CAD design and consulting, and also CAE or simulation as well. Next is just a quick introduction of myself. My name is Sheyi Shambore. I got a couple of bachelor's degrees and then a master's, all in about 6 years from 3 different schools. And then I started working here at Boundary and primarily focus on, CAE analysis, simulation, those kinds of topics. And for me, it's fun. It's wonderful. It's always great to have to use computers to test the limits of customers' designs and then show them how they can improve long before they've even built a physical prototype. So I hope I get to show you some of that today then. All right, so we're going to start off here with Creo Simulate. Now, Creo Simulate, I think a lot of you are familiar with it, from a conceptual sort of, background of, it's a software that comes with the Creo and you use it to run simulations, and what that entirely means or entails. It's almost left for interpretation. So I'll go ahead and explain some of that. So Creo Simulate is an app that comes within the Creo package. So many of you are familiar with Creo Parametric. That's the most common CAD package, at least when it comes to design or building your designs. One of those other apps that comes along with the Creo apps is Creo Simulate. And Simulate basically has a very similar, environment or UI as Creo Parametric, but it allows you to test your model for things like, the impact of, forces or stresses on your design, or if you have, in the case of a, non-linear kind of if you have, in the case of a non-linear kind of design, testing, for example, the deformation of a rubber gasket, as you deform it into a seat, and then also, for example, running dynamic analyses, seeing, what your modal frequencies of your design are, so basically what the modal response is, or if there's a frequency range that's going to excite your model. Having implicit simulations where you have your force varying with time, and then you could see how your model responds to that, where your maximum stress or displacement is. Also running things like fatigue analyses. Excuse me one second. Yep, sorry about that. Just had to cough a little bit. Yep, also running things like fatigue analyses where, you can test out the impact of not, a slow or steady sustained loading over a long period of time, but rather a repeated loading and unloading cycle of a medium to low impact load over a very long period of time, and to see, how does fatigue play into things? How many cycles do I expect this, steel design to endure before I have crack initiation? Things like that are questions you can answer with Creo Simulate. Other kinds of questions are things like running thermal analyses and being able to see how, for example, if you have a heat input at a certain section of your model and you have some sort of heat dissipation, say for example a radiation or what's it called, a convection coefficient. Having those kinds of things, you can begin to test out, okay, what's the maximum temperature my model is going to get to, or how long will it take my model to cool down or the design to cool down? Or you can even begin to analyze things like, given a particular temperature, what's the resulting thermal expansion, and will that thermal expansion have some sort of, huge impact when it comes to either deflections or stresses, right? And then finally, the beautiful part of it is the design optimization, and that's one I love to stress with Creo Simulate. Because Creo Parametric itself is a parametric CAD design tool, that then means that, and because Creo Simulate is an app of the main Creo interface, that then means that first off, Creo Simulate and Parametric are already coupled together. And that means that for many of the analyses we specified up top, you can very simply define an analysis, or basically a design optimization, to go back into Creo Parametric and change a dimension, and then come back into Creo Simulate and rerun the same analysis you just defined, and then to either keep rerunning or stop running, or make a value judgment based on a certain criteria. And if you think about it, in your life as a design engineer, that is, 90% of what you'll do with simulation. 90% of what you'll do is running a certain analysis, and based on, the stresses or the fringe plots or the temperatures, going back into your design, making a slight change or modification if it's not satisfactory, and then coming back into simulation and rerunning it again. And so the fact that you have an automated way of doing that for you is pretty incredible. And it's definitely one of the huge benefits of using Creo Simulate. Yep. So for this particular session, sorry, hold on one second. Just need to cough a little bit. All right, so for this particular webinar, we're going to focus on two specific analyses. First is a linear static analysis, and next is a thermal analysis. And so we'll focus on how to run both of those, again, showing you some examples. But again, just so you know, all these other analyses you can perform them very easily in simulation, in Creo Simulate here. We're just going to highlight the linear static and the thermal analyses. All right, so at this point, I'll pause here and switch to a demonstration of the software. All right, so what we have on screen right now is a drone. It's a quarter symmetry model of a drone. And before I actually go ahead any further, I'll go ahead and give recognition to whom it's due. This model is something I grabbed from GrabCAD from a person called Amamu Madi, and so just want to recognize that. And so he created a model of I want to say it's a first-person viewer, very small quadcopter drone. And we went ahead and just took that particular model and we did a little bit of cleanup. We removed, some of the, extraneous components that weren't adding as much weight or stiffness to the model. And then we also, chopped this in a quarter, basically. So you'll notice this is a quarter of the full model. Now the reason for that, the reason for chopping it into a quarter is so that way, have your normal, the reason for chopping it into a quarter is so that way we can basically use quarter symmetry to analyze the model. And again, that's one of the benefits of Creo Simulate, is that it's very simple and easy to use for a design engineer, and yet you can do many of the complex things that you can do in many other advanced simulation packages as well. And so in a case like this, you can very simply cut this model into a quarter and then go ahead and get into Simulate and then start analyzing this quarter symmetry model here, knowing that the same fringe or stress pattern is going to be repeated across the entire 4 other quarters of the drone. All right, so we'll get into Simulate here, and we'll simply get in by hitting Applications and then Simulate. Now, right now, you'll notice first off, we're still in Creo Parametric. And when I hit Simulate, it's going to load in the new application. It pulls us into Creo Simulate. You'll notice that it still says Creo Parametric over here, but our user interface now looks very different. We don't have tools telling us to extrude and revolve anymore. We now have tools telling us to, create a force or displacement constraint, or, define analyses and things like that. And so again, this is to show that all within one embedded interface, just with the click of a button, you can switch from one powerful software to another. With the same environment that you're typically used to, and so this requires much less a learning curve or ramp-up time, and you're able to get up to speed, much easier because, again, it's a familiar interface that you're used to, and so this makes it much easier to use. All right, so next up is, defining our analysis. Now, one of the, tips or tricks I like to show for, very, very new beginners in simulation is what's called a process guide in Creo Simulate. And so if I go ahead and start this here, I'll go ahead and click Run Session. And we'll go ahead and click the Static Analysis Native over here and say OK. Now, this process guide is a very simple, as it's called, a process guide that walks you through how to perform specific analyses in Simulate. Now, this is a guide that is fully customizable. You can, add or remove different areas from this, or you can even create new process guides for new kinds of analyses as well. And so this is a case where, for more advanced, CAD administrators or super users, you can create a process guide specific to your company's analysis, process, embed that into Creo Simulate, so that way younger or more green design engineers or even interns can still follow the same step-by-step process and achieve, similar results that you would as well. But again, I like to show the process guide because it basically shows you the minimum, requirements you need for a simulation. And so that's one of the things where, people usually ask a lot of times, whenever I start in Creo Simulate, I don't know what to put in because it's just a whole big black box and I'm not sure what to click, and I'm scared if I click something, it'll all go haywire. Well, the easiest way to combat that is to look at the process guide. And so whatever the process guide just tells you is what you specifically add into it. Now I'll have this on the side here. I already have the model set up, but I'll walk through the process guide to show you what's going on. So first off, it says to have materials in the model. And so we'll go over here and and assign our materials. Now in this case, our materials are already assigned, so if we go ahead and take a look at these here, yeah, so we'll notice that in this case, the motor housing over here and also the propellers are both made out of ABS plastic, right? Say OK, and then we'll pick on this over here, and yeah, so we'll notice in this case the I'm not sure what you call this piece over here, but this arm that basically holds the motor is going to be made out of steel, and so we'll keep that as OK. And then finally we have this particular piece over here, and that basically is a material we call that battery. Now again, there's really no real life material called battery, but that again goes to show you that you can very easily customize your materials in Creo Simulate. In this particular case, what we have is one material that has an aggregate, density for what a typical battery would be for an FPV drone racer, and not only that, you're having also what's it called? A representative Young's modulus of how that battery would deform under stress, and that's really what we need to specify those requirements here for the battery material. Next, it says that we need a load set with loads in it, and so we'll go ahead here and take a look at our load set and realize we already have a load set. And for the loads, what we're going to do is let's do this. I'll pick on this over here and analyze this. And so you'll notice over here that the load is basically the lift force applied over the surfaces of the propellers. And in this case, we know that based on the speed of rotation of these blades, we're going to get about 2 newtons of lift, generated by each of these propellers. And so we can very simply put that in there. And now again, another trick I usually like to show, is that with Creo Simulate, it's very easy to use, and so you can very simply convert from one unit to another very easily within Simulate right here. So if this is something where I want to convert to or enter the quantity in pounds, I can very simply change my units right there, and Creo Simulate will do the conversion in the background. I believe this was newtons. Another thing I could do is I could say, okay, well, right now it's 2 newtons. What is that in pounds force? I can right-click in here and just say, hey, let's convert that to pounds force and see. Okay, that's what it gets me, right? And so I can convert that back and forth to whatever unit I like, without having to open up Google or having to remember what the conversion unit is, conversion factor is between pounds and and newtons, for example. All right, so we'll go ahead and so we're done defining our loads. Next is our constraints, and so we already have a constraint set defined. Next is to define the constraints in there. Now the constraints we're going to define are going to be this. So because this is a symmetry model, we're going to define constraints for typical symmetry, which is going to be this. So I'll pick on this over here. Now mirror symmetry in any in almost any simulation package requires to have basically a planar constraint. So in other words, to have the direction of translation normal to the surface fixed, and then the 2 orthogonal rotations fixed. So in other words, in this case, let's do it this way. That. All right, so I'll show it this way. So basically what that means is if I'm going to make these surfaces here, symmetry, then that direction is the x direction. And so I want to fix the x direction translation-wise. And then I want to fix the rotation of the y and the z directions. And now you'll notice at the moment I do those three things, what I basically have is a planar constraint. What I basically have is something that can only move in plane but not out of plane. So in other words, if I had, this side of the drone resting on a table, then I could not move it, in that direction without violating that entire surface having to rest on the table. And I could not rotate it, off the table without having to violate the, y or z rotations being constrained on the table as well. And so that's the reason why for this particular one here we use a planar constraint to fix all those different surfaces. Next is over here on the left-hand side, we basically did something similar. The only difference is instead of using a planar constraint here as well, we now use in this case a specific constraint called the symmetry constraint. And in this case, we picked a similar set of surfaces, and the symmetry constraint will do basically a similar thing to a planar constraint. Is it will fix the two orthogonal rotations and the translation in the normal to the surface you select. So again, there's really nothing special about selecting a planar constraint in that first instance. It's really just a matter of understanding what the planar constraint is doing and if that's applicable in this particular case. And it is, and so that's why we use a planar and a symmetry to constrain this model. Now, not only that, based on what we have right now, this model can still move up and down even though it's constrained with those two symmetry constraints. And so the last thing we're going to do here is to add a displacement constraint to just that bottom point at the back over here and fix it vertically in the y direction. And this is more than anything just to allow for solution stability, to make sure that our model is sufficiently constrained. And then not only that, that is also because we're analyzing this at one snapshot in time. And so we can basically assume that the entire drone deforms relative to that point over there at the bottom. So we have constraints. Next is we're going to create our analysis and then run the analysis. And so we'll go over here and see analysis and studies. And to create an analysis, it's as simple as clicking over here and just say let's have a new static analysis. And we can define whatever we want. We can check the boxes for our constraint set and our load sets. Usually single pass adaptive is adequate for a lot of what you do. And then we could just say OK and then hit the green flag to run. And so I like to show this process guide because it walks you through what you need to define an analysis. Right. Now another trick I like to do whenever I run and Creo Simulate, particularly for models with assemblies, single parts not so much, but assemblies I almost always do this, is I run what is called a constrained modal analysis with rigid mode search. And so if I go ahead and take a look at this here, I'll go ahead and show you what I'm talking about. So I basically select a modal analysis. I select this here to have it constrained, and then I check this box to say with rigid mode search. And then I probably increase the number of modes to, say, for example, 10. Now the reason for that is this. For any linear static analysis, we always want to make sure that our model is sufficiently constrained so that we can't move freely in any X, Y, or Z translation or rotation direction. In the case of an assembly, because there are many different parts, having to manually check to make sure that all these different parts are connected to each other properly, so that way they are all sufficiently constrained, could be time consuming. Again, if you have 2 parts or 5 parts or 6 parts, it may not be as bad, but with an assembly of 20, 30 parts or even more, it becomes very tedious. And so what I do is I run a constrained modal analysis with rigid mode search. And when I'm taking a look at the results, I begin to look for any frequency modes with a frequency of 0. Because again, that tells me that that's a rigid mode. That tells me that at a frequency of 0, this particular object can move, freely in that direction. Now so if I had a frequency of 0, for example, I would check that particular frequency and go under here for display options. I would check deformed and I would animate, and then I would hit OK and show. Now, usually what that would then show me is one particular direction where the drone was moving, freely. So in other words, if this mode was a 0 hertz, I could probably then see it moving up and down, in this direction. And then I would understand, okay, well, the Y direction probably needs fixing, and so I would then go analyze the model. Or something that's even better, if one component was not properly constrained, that single component will wiggle in that direction. And so again, that'll give you insight as to which component is not properly fixed. In this case, everything is properly fixed, and so that's why I don't see any singular translation in one particular direction. It's translation in multiple directions as I animate that rigid mode, so I know that everything is properly constrained. And again, I just run that analysis not so much as a core thing to extract results out of. It's really just a sanity check to make sure that my setup is correct. And so in this case, for a static analysis, I'll go ahead and take a look at some of the results we have. And we'll look at a stress, for example, and and take a look at that. And now we can very easily see, okay, how stressed our model gets as it starts rotating, right? So as the propeller starts spinning, you have 2 newtons of lift generated on the blades over here, and then we also know that in this particular case, the blades don't deform as much as is shown on the screen here. The deformation is basically magnified, so that way it's more apparent or visible. But again, you'll notice as the blades would deform upward due to the upward force from the lift, right over here in this corner, it looks like is where we have our maximum stress, right over here. Let me see if that's also repeated at the bottom as well. Yeah, also at the bottom as well. And now the maximum stress is about, I don't know, it was about 33 megapascals, which for ABS plastic, I don't know, that could go anywhere from 43 to 43 megapascals yield. So technically we're safe. The other thing I also like to do whenever I interpret these results is to basically use some common sense. Right around sharp edges or sharp transitions, you basically have in simulation what's called a singularity. You basically have, an almost, this is basically a line, so an almost zero area, entity mathematically. That has a force passing through it. And so right around lines or singular edges, you will have sharp stress concentrations as well. That will dramatically drop the further away you move from the area. And so is this to be expected for the region I'm in? Yes, I would say so. The other thing is this: in reality, is my 3D printed or my manufactured ABS plastic propeller going to have an exact sharp edge right over here? No. There's going to be some very, very tiny radius or fillet that we're going to put of some certain number. And so that stress concentration in that area is not going to be as high. And so again, this shows you from a logical perspective, yes, I can expect this area to be highly stressed as the entire propeller deforms upward and this area is more rigid. Yes, I can expect this to be more stressed, but for me to get almost close to the yield of ABS plastic may not be, as realistic. And so I show this to show you, in terms of interpretation-wise in simulation, it shows you some glaring things that you can take a look at, and you can see if huge areas of your model are above your yield. But again, you don't always want to go by the highest value of stress and say, oh my goodness, this is going to yield, because you may be dealing with some singularity issues that you want to be aware of and take notice of. All right, next is going to be thermal analysis, and for that we're going to switch over to this over here, this model. So this is a simple model of a brake system, and what we have in here is the brake calipers and a whole bunch of other components. We have bolts and all of that. We'll basically defeature all of this using a simplified representation in Creo Parametric. And again, this shows the beauty of coupling Creo Parametric and Simulate. Is now we switch to Creo Simulate with the click of a button, and now we still have our defeatured model. The difference now though is we clicked on this button here for thermal mode, and so now we can put in thermal effects. And so for example, we'll put in over here that there's a certain heat load coming into that brake disc based on the heat it takes to based on what's it called, the stopping force required to stop a car that's I don't know, at 60, 70, 80 miles an hour down to zero. And so we have that heat input coming in over here, and then next is we know that in this case part of what we're trying to design for is we're trying to have all of these different fins act as heat dissipation areas. And so we're then going to say, well, let's put in a convection coefficient across those fins, because air is basically going to be passing through those fins in order to help dissipate the heat. And so we specify a convection coefficient of basically not so much ambient air, but air that's moving moderately moderately faster than ambient, but not very, very fast, just so that way we can get a worst case scenario of how it'll cool down. And yeah, and then we'll go ahead and take a look at the results in this case. And actually in this case the analyses have already been run, and so I'll go ahead and take a look at what's it called, a steady state analysis result for this particular model. And basically this just shows assuming that the forces apply, or the heat load is consistently applied as is, and the heat is dissipated consistently as it's currently being done, we can expect to have a max of about 400 degrees F, with a delta of about 20 degrees on this brake design. And again, the cooler areas are the areas that where heat is dissipating out of, which is basically those fins. Now, is 400 degrees realistic for what's it called, a brake disc, and how hot it gets? And the answer to that is actually, it depends on the brake you're talking about and the car you're talking about. It's not uncommon to have performance cars like Porsches, for example, experience such high temperatures on their brakes. And so again, this goes to show you that you can very simply use Creo Simulate to run either linear static or thermal analyses, get some results out of it, and then based on those results, be able to interpret, or get a better understanding of your design. All right, now why does all of this matter? Well, all of this matters because first off, with simulation, you can very simply shorten your time to market because this allows you to test multiple different variations of any design on a computer long before it's ever built. You can also reduce your design cost because you're no longer having to spend dollars building 5 or 8 prototypes of your designs. You can test all 8 in a computer, realize that the first 5 are basically useless, and then only physically test the 3 that give you the most value, right? And then based on that, you can also then improve your design quality because you can test out many different variations of your design in Creo Simulate that you wouldn't be able to build all of those or test them out in reality, or at least it'll be more cost prohibitive to build physically. But because you can build them in a computer, you can churn them out all day long and begin to analyze, and see how you can improve your models. So just a quick example I like to talk about regarding the, shortening the time to market or reducing the design cost. We had a customer approach us once talking about them trying to simulate the opening and closing of a door hinge, or basically the forces on a door hinge. And they mentioned that right now they basically have it basically takes them about 2 to 3 weeks to build a prototype of the door hinge design, and then they strap it to this test assembly, and they have this robot that basically sits there and opens and closes that door, I think about once every second or so, for about 3,000 cycles. And so they basically spend 2 or 3 weeks, a couple $1,000 building a hinge, and then sitting there waiting for about 2 weeks while this robot cycle tests their hinge to, however many cycles they need. And then once they're done with that, they remove it off and then put another hinge on, and it's the same thing over and over again. And you can imagine that, simulation will, dramatically reduce, the time it takes for them to test each hinge design. And not only that, reduce your design cost as well. And yeah, so we'll go ahead and move on from here. All right. And so just to talk about a couple different, case studies or examples out in the field where this has actually been used. President of American Wave Machines, they make these, wave machines out in California. And talking about, virtual prototyping or basically simulation has helped speed up their, product development, and now they're able to, produce a more competitive product, a much more quality product, which basically, led to 30% sales growth year on year for them. Another example here is what's it called? A director in Bang Design, which is a very, very famous design firm based out in India. And they testified to using simulation during concept design, and they're able to explore 30% more options than they were able to before, using simulation, because again, it with a shorter time to test out the design and more flexibility to do so, you can test out a ton more stuff, and so that way you can, dramatically improve your design and also directly impact your bottom line as well. All right, so if you need any more information or have any more questions about Creo Simulate, my contact information is right there on the screen. And if you need any sales information, you can email or call Steve Seymour at the bottom over there. Also, if you have any thoughts or ideas about future webinar topics you'd like us to consider regarding simulation, if you watch this webinar and you say, hey, I appreciate this content, but I'd really like them to talk about using Creo Simulate to do this other kind of analysis or this other kind of topic or whatever else it is. Please don't hesitate to shoot me an email, and we will definitely consider your input in further simulation, further webinar topics regarding simulation. Thank you so much for your time, and you'll have a good rest of the day.